Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's a great pleasure to introduce Harry Zhu from Ohio State University. Harry is a PhD student, and he's going to graduate this year, so he's here to talk about his PhD work. Harry had some great internships at IBM Research, and some of the two internships sort of prompted his line of thinking around understanding how programs use memory and the aspect of memory bloat, which he's actually investigated over the past few years with a number of really interesting publications. Harry's received several awards, including an IBM Research Fellowship, a fellowship at a Distinguished Paper Award at ICSE, and also a departmental fellowship at Ohio State University. So with that, I'll introduce Harry. Thank you for coming.
Thank you. Thank you, Ben, for introduction. So it's a great pleasure here to talk about my research. So let's get started, maybe. I'm actually a program analysis person. I'm interested in both theoretical foundations, program analysis, and its applications. So important application that forms the basis of my PhD thesis is to use static and dynamic program analysis techniques to help programmers find and remove what we call runtime bloat in modern object-oriented software. So this research here is motivated entirely by the real-world problems that we have regularly encountered and studied. So here I'm going to tell you the story. All right, so as probably all of us here have already seen, the past decade has witnessed a tremendous increase in the size of software, which now contains more and more functionality and consumes more and more resources in order to solve increasingly important problems. So this picture shows the growth of the total number of objects in the heap in the large Java server applications over the course of 2 years between 2002 and 2004. So the total number of objects in the heap has increased, for example, from less than 500,000 in the beginning all the way up to 30 million then, like more than 60 times over this 2-year period. So what happened to this application? Why does this application have consumed so much memory now? Because now we have this big pile-up thing. So this picture shows the architecture of the SAP, the SAP NetWeaver application server, where each box in this picture represents a component of the server. So this application server has millions of lines of code and needs about 20 components to work simultaneously in order to function. So one important thing that can be seen from this picture is that this application server itself is a big pile-up, right? It's built on top of layers, frameworks, and libraries. So first of all, it can be extremely easy for such a large-scale, framework-intensive application to suffer from performance problems. So for example, suppose there exists small performance issue in one of the components here. Its effect can quickly get orders of magnitude more significant when those components become nested and layers, right? And second, if this application has a small performance problem, it will be extremely hard for their developers to find why, because the problem can easily cross many layers of libraries and frameworks. And those libraries and frameworks can come from different vendors. In most cases, their source code is not available. So as a result, significant performance degradation and scalability problems can be regularly seen in large-scale and real-world applications. All right, so a lot of evidence has been shown that most performance problems in modern object-oriented software are caused not by the lack of hardware support, but instead by runtime redundancies or inefficiencies during the execution. So we call those general redundancies or inefficiencies runtime bloat. A typical example of bloat is to use a very complex heavyweight function to achieve a very simple task, which should have been achieved in a much easier way. Bloat has caused applications to consume increasingly large memory space. So for example, a typical Java application, Java heap, has quickly grown from, for example, 500 megabytes a few years ago to 2 to 3 gigabytes today. It's very common. But it doesn't necessarily mean that we're now supporting more users or functions, right? So here's a list of common bloat effects that we found in real-world applications that we have studied. So for example, a large-scale application originally designed to support millions of concurrent users can eventually scale only to thousands of users in practice. And it was extremely hard for their developers to find out the reason. So they gave it to IBM Research for performance tuning. As another example, the designer of a large-scale application initially expected only 2 kilobytes memory for saving session state per user, but eventually they found 500K, for saving session state per user, more than 250 times larger than they initially expected. So the consequence of bloat is not just excessive memory usage. Large memory consumption usually comes with the execution of a lot of redundant operations that can cause a significant slowdown of the application. So bloat can have huge impact on scalability, power usage, and performance of large-scale, real-world applications that form the backbone of modern enterprise computing, used every day by thousands of businesses. Bloat can also have a huge impact on mobile computing, where most applications have very strict resource constraints. According to IBM Research, millions of dollars are spent every year by its customers on memory, like bloat detection, like performance tuning, and memory leak detection. So that's why IBM Research is pushing very hard to develop useful tools that can help programmers identify performance problems. All right, so what can we do? What can we do to deal with this ever-increasing level of inefficiencies? The first thing that we can probably think of immediately is to use compiler optimizations. The programmers, people's general feeling is like this. We don't need to worry about performance in object orientation because we have this advanced compiler technology. We have this garbage collector, right? So let's leave it entirely to the compilers and the runtime systems because they are always smarter than ourselves. That's basically what people think in the real world. However, the usefulness of those traditional compiler technology is very limited in optimizing bloat away because a general data flow in large-scale application can easily cross thousands of method invocations, many layers of libraries, and even frameworks. This is a very large scope, way beyond what the compiler analysis would inspect. And of course, optimizing a lot of real-world problems may require a lot of developer insight, which the compiler doesn't have. On the other hand, it's not easy as well for the human experts to perform manual optimization, primarily because of a lack of good tools that can help them make sense of large heaps with millions of objects and long executions that can last for hours and days. So my entire thesis here is to find a better way that can identify larger optimization opportunities with a small amount of developer time. How are we going to do that? The basic methodology is to advocate compiler-assisted manual tuning in order to take advantage of both sides, the manual optimization side and the compiler side. Specifically, I've designed, implemented, and evaluated static and dynamic program analysis techniques that can first identify the root cause of a memory problem or a performance problem. And second, remove automatically or manually some kinds of bloat patterns that we identified with these techniques. And third, prevent bloat from occurring in the early stage of software development. So this is actually a three-step approach. All right, so our techniques were implemented on a variety of different platforms. So, for example, the dynamic analysis were implemented on JVM, the IBM G9, which is the commercial JVM of IBM, JXRVM, which is the open source JVM written in Java, and also use JVM-TI, which is like general tool interface supported by all JVMs. And the dynamic analysis can be used to generate online bloat warnings during the execution of the program. The static analysis were implemented on Suit, which is a popular program analysis framework for Java. The static analysis can be used either to produce to produce bloat warnings or to generate refactoring suggestions during coding when the developers write their code. So this really demonstrates that our techniques are general enough and they're not limited by any specific platform or framework. All right, so this slide shows an overview of the set of techniques that I have developed for my thesis. For example, for dynamic analysis, we start with profiling the execution to identify certain bloat evidences, like a lot of copies, large cost-benefit ratios, high memory leak confidences. They're all strong indicators of bloat. And then by analyzing the profiled activities, we generate bloat or memory leak report. For static analysis, we analyze the bytecode of large-scale applications to identify certain bloat patterns that we have previously found using the dynamic analysis in order to either generate bloat warnings or to transform the program to produce optimized code. So for example, static analysis can be used to help programmers to identify bloated containers. They can also be used to help programmers find and hoist loop-invariant data structures. So in addition to software bloat analysis, I've also contributed to some other program analysis areas. So for example, I'm very interested in scalable point-student data flow analysis. I've done some work on control and data flow analysis for aspect-J, which is the major aspect-oriented language. I also have some experience with language level checkpointing and replaying. In terms of research areas, my work goes from very high-level software engineering across programming languages, compilers, all the way down to runtime systems. So this slide should give the detailed classification of the publications in terms of research areas. So I actually have experience and expertise in these three areas. So now we're done with the introduction part. Now let's get a little deeper into the technical problems and solutions. So here, I'll talk about two specific program analysis techniques to help programmers find and remove bloat, one dynamic analysis and one static analysis. The goal of the dynamic analysis is to find low-utility data structures to help programmers do performance tuning. The static analysis can be used to help programmers find and hoist loop-invariant data structures. So the goal, the motivation of the second static analysis is based on a lot of loop-invariant data structures that we found using the first dynamic analysis. That's how these two analyses are connected. So eventually, I'm going to talk about the future work and conclusions. All right, so this is the first piece of work, which was published in PLDI, one of my PLDI 2010 papers. The goal of this analysis is to identify high-cost, low-benefit data structures that are likely to be performance bottlenecks. So how are we going to do that? We design a runtime analysis that computes a cost measurement and a benefit measurement for each data structure in the heap. And eventually, we present to the user a list of data structures that are ranked based on their cost-benefit ratios. Intuitively, data structures with high cost-benefit ratios are likely to be closely related to performance problems. That's the motivation. All right, so before getting deeper into the technical problems and the solutions, let's first go through this motivation part. Yeah, sure.
So you're talking about the cost, but in fact, the cost of extra memory isn't. There's sort of this subtle indirection in the sense that the cost of extra memory isn't visible unless you notice performance effects from it. Say, for example, it's bigger than the cache, etc.
Oh, yeah.
So, how, do you get to, when you talk about cost? Do you get to the actual cost in terms of the impact on cycles, or do you actually is it just
cycles.
More memory is better? Worse,
right. So I think its cost benefit is defined in terms of the actual computation done instead of the amount of memory needed used or something. So it's like more about execution bloat or instead of memory bloat.
Okay.
So.
So I'll let you go. Just to clarify that.
Okay, sure. So, this is actually, let's first go through the motivation. As we probably already know, runtime bloat can manifest itself through many observable symptoms. So, for example, a lot of temporary objects that are really short-lived objects, right? They're not long-lived. A lot of pure data copies without any computation done. And maybe, a lot of highly stale objects, meaning objects without any, that are not used for a long time. And many problematic containers. Maybe many other symptoms that we're going to observe in the future. However, in any tuning task, it will probably be impossible for the developer to try all those different techniques, look at all those different symptoms to identify a performance problem. So that basically doesn't make sense. An immediate question to ask here is there a common way? Or in other words, more systematic way, beyond all these different symptoms and techniques that can characterize different kinds of bloat, even though they could exhibit different symptoms. As bloat is really about runtime inefficiencies, we found that what is really common about different kinds of bloat is that there exist operations that are very expensive, very hard to execute, but do not produce data values that have large benefit or impact on the forward progress. In other words, the costs of those operations are out of line with their benefits. This observation actually motivates us to compute this cost-benefit measurements to help programmers do performance tuning. So how are we going to do that? Let's first look at the example. This example shows a problem that we found from Eclipse framework using our dynamic analysis. So here's a method called isPackage that takes a Java string as input and eventually returns whether or not this string represents a valid Java package name. Right? The way this method is implemented is that it first calls another method called directory list in order to identify and return a list of all files in this current directory represented by S here. And then it checks whether or not this return list equals null. So it's easy to see that there's a much easier way or smarter way to implement this method, right? So for example, we can directly parse this incoming string into two parts, like Java and IO, and check directly whether or not they correspond to valid Java directory names, right? So we don't necessarily have to find all those files in the directory. So in this case, for example, this big list data structure pointed to by this variable packs has the highest cost-benefit ratios because intuitively there's a lot of effort made to identify those files and populate this entire list, but eventually none of the elements in the list are used for any purpose. So the cost-benefit ratio is the highest. So for this example, this example actually shows a typical problem with the current object-oriented programming practice. So for example, the programmers are encouraged to pay more attention to high-level abstractions, like modularity, reuse, readability, without considering performance. So for example, in this case, think about why the programmer wants to do this. Why the programmer wants to implement this method in this way. The only reason that I can see here is that the programmer just wants to reuse the implementation of this method directory list instead of creating a specialized, simplified version for it, right? However, they're never aware that this piece of code can be executed for millions of times. And when this list becomes large, it really hurts performance. In fact, by simply creating a specialized version for this method, we were able to reduce the running time for this application by 8%, which is very impressive. All right, now let's go back to the definition. So what is called? Yeah, sure.
Was the 8% easily apparent in the profile, or was it hidden by its much of the cost being effects on garbage collection and stuff like that?
Well, I think generally I think it's the algorithm problem.
Yeah, but if someone looked at it decided I care about the performance of this program, I'm going to go look at the profile. Would they have been
identified the problem by looking at the simple profiles?
At least would they have been told to look at his package, or would it have been spread out by mostly secondary GC costs or something like that?
Well, we don't have sort of a detailed profiles of the like what percentage of the 8% comes from the GC and what percentage comes from.
Just asking if you just used a very simple technique for just profiling the amount of time spent in each method.
Oh, okay.
Wouldn't this directory list pop up?
Well, actually, if you look at the GC, the simple profiles of the running time profiles of the large scale application like Eclipse, there's I'll give you a very specific example. So if you look at the large scale applications, like we have done this profiling for this large scale application, we found that the most frequently executed method for this big application is a method called hashmap.get. So it turns out that the methods like that can never be the most executed method, most frequently executed method.
Would it have shown up as 8%? You would have seen, 8% is for this little tiny isPackage thing. I'm going to go look at that.
No, the profile cannot say. If you look at the running time profiles, it never shows like 8% for this method, right? I don't know. Because of cost, yeah.
GC costs associated.
Yeah, there are a lot of different things going. Yeah, there's no. Yeah, so that's probably the answer, right? Okay. Yeah. Okay, now let's go back to this cost-benefit thing. So what is cost and what is benefit? So the absolute cost of a heap value here is defined as the total number of instructions executed to produce a value. So each instruction here has a 3-address representation, like A equals B plus C, and each instruction here is considered to have unit cost, right? So that part is really easy to understand. And then, so it's a little tricky to define what the benefit is. As the benefit of a value is really related to how good the consumption of that value is, right? So there's no clear metric for that. So here I'm going to give you some intuitive definitions of benefit. And later, I'll talk more about the formal definitions. So intuitively, a benefit of a value is defined as a very large number if this value, this heap value, goes to program output, like socket or file system, because it's actually used for any purpose, for some purpose. Of course, the benefit is 0 if this value, this heap value, is never used. The third case here is the most common case, where this heap value is used to produce another value, another heap value, v prime. In this case, the benefit of v is defined as the amount of work done to transform v into v prime. So there's some kind of relationship between the cost of v prime and the benefit of v. So again, these are just intuitive definitions. I'll give you more more formal definitions later during the talk. So first, let's look at the cost computation. How can we compute the cost? A natural idea to compute the cost for a program like this will be to capture a dynamic dependence graph, that looks like this one here, right? Where each edge represents the data dependence relationship between a pair of instructions, one writing to a memory location and the other reading from the same location, right? So for example, suppose now we want to compute the cost of a D here. It can be computed efficiently by traversing backward this dependence graph and counting the total number of reachable nodes, which represents the total number of instructions executed, right? Which is actually 4 in this case. So we call this problem a backward dynamic flow problem because in order to solve the problem, we need to record and traverse backward some kind of history information of the execution. So this is a backward problem as opposed to a forward problem, right? There are actually many, many other backward dynamic flow problems. This is just one of them. If you're interested in those other problems, you can look at the paper, or we can talk offline. So in general, the only way to solve this backward dynamic flow problem is to use dynamic slicing that captures a dynamic dependence graph that looks like this. So for example, dynamic slicing is actually a general dynamic technique that needs to record all memory accesses and during the execution and their dependence relationship, right? So it's easy to see that dynamic slicing is prohibitively expensive for large-scale and long-running applications because the trace it generates, the dynamic slicing generates, is unbounded. It depends completely on the dynamic behavior of the program. So it's prohibitively expensive. However, so in order to achieve efficiency and make our analysis more scalable, we propose a new technique here called abstract dynamic slicing that performs dynamic slicing over bounded abstract domains. So the motivation of this new technique is as follows. If we look at a specific client analysis that uses the result of the slicing algorithm, the trace generated by dynamic slicing usually provides many more details than this specific client would possibly need. So a natural question to ask here is that, is it possible to let the slicing algorithm be aware of this client analysis so that it can capture only part of the execution that is relevant only to the client? In other words, we wonder whether or not it's possible to customize the client analysis, the slicing algorithm with the semantics of this client analysis. The answer is yes, and we do this by looking at abstractions. So we found that for many backward dynamic flow problems, equivalent classes exist. So here's a simple example that shows a fragment of a program trace that contains different runtime instances of the same instruction, A equals B.M. Each instruction instance here is annotated with an integer I that represents the ith execution of that instruction. So given the client analysis, a specific client analysis, it will be possible for us to divide those runtime instruction instances into two equivalent classes, like E1 and E2. So later, it will be sufficient for the client analysis to look only at those equivalent classes, E1 and E2, instead of looking at individual runtime instruction instance. So in this way, we can potentially record only one runtime instruction instance per equivalent class as its representative. That can potentially lead to a significant reduction in the amount of memory needed, right? It's easy to see here that the dependence graph computed this way is an abstract dependence graph, where each node represents an equivalent class, and each edge connects two equivalent classes as long as there exists a dependence relationship between two runtime instruction instances aggregated into their equivalent classes, right? So we've actually generalized this idea and defined a more general theoretical framework that can be instantiated to solve many, many other backward dynamic flow problems. This talk focuses only on high-level ideas. If you're interested, yeah, sure.
So how did you define the equivalence classes?
Well, I mean, that's, user has to provide some kind of annotation. Like the designer of the analysis gave the semantics of the analysis, so that our analysis, our profiling framework takes the semantics as input and defines those equivalent classes.
Can you give us one example?
Yeah, I'll give you a specific example. Sure, of course. So what's your question about? No, about
same thing.
Okay, sure. Yeah.
Example would help.
Oh, of course. I mean, here's the example. So let's look at go back to cost computation. How we're going to use abstract dynamic slicing to compute cost for a specific runtime value. So recall that the absolute cost for a runtime value is defined as the total number of instructions executed, right, to produce the value. So here, for example, the absolute cost for a specific runtime instruction instance, like this one, A equals B plus C, annotated with 20, can be computed by traversing backward this concrete dependence graph and counting the total number of reachable nodes, which represent the total number of instructions executed, right? Right. That's basically for absolute cost for the concrete dependence graph. However, as we already know, concrete dependence graph is very expensive to compute. In addition, it's very hard for the programmer to make sense of a specific runtime instruction instance, because the static instruction can potentially have millions of runtime instances. So it doesn't make sense for the programmer to let the program make sense of the cost for a specific one. To solve the problem, though, instead of computing this absolute cost for a specific runtime instruction instance, we propose to compute abstract cost for an equivalent cost of instances. So for example, the abstract cost for an equivalent cost, like this one, A equals B plus C annotated with E0, can be computed by traversing backward this abstract dependence graph and calculating the sum of the sizes of the reachable equivalent classes. Right? The size of an equivalent class is essentially the total number of instruction instances aggregated in that equivalent class. So in this way, we can easily find that, first of all, abstract dependence graph is much easier to compute, and second, it's easier for the programmer to make sense of it, because the abstract cost for an equivalent class is essentially the absolute cost for a set of runtime instruction instances aggregated based on some kind of abstractions, right? Now the question is, what is the appropriate abstraction that we can use for computing cost here? That's basically you guys' question, right? So, all right, so here we use calling context to define equivalent classes. In other words, those E102, E47, E0 are object sensitivity-based calling contexts. Specifically, each of the E here is a chain of receiver object allocation size for the call size on the call stack. In this way, it will be natural for us to aggregate runtime instruction instances based on object-oriented data structures. So if you're interested in object sensitivity, we can definitely talk offline. That's basically the general idea. Okay? Yeah.
So if an instruction appears in a loop, you will count it only once for that calling context, even if it's executed 1 million times.
Right. Loop, I mean, we only consider the method cost, like the chain of the object.
So the cost can still be very skewed away from the action cost.
Oh yeah, there's still like different. Yeah, sure. Yeah. But this is not very accurate. I mean, it's like approximation.
I mean, is it always under approximated? Or it could be over approximated too, right?
I think it's always over approximation.
No, I just gave an example. It's under approximated, right? If it's a loop, if it's an instruction inside a loop, you will count it only once based on the calling context, even though I execute it 1,000,000 times because I go around the loop 1,000,000 times.
You go around the loop 1,000,000 times, but the aggregate. I mean, the cost is actually the frequency, right? It's considered the frequency of that.
You will count the number of times I execute the instruction.
The trick here is he wants to limit the number of the size of the dynamic.
I understand.
Yeah.
Set, right? So he's going to have, you're iterating 1,000,000 times over like 1,000,000 objects, say, but the call stack remains the same. So you're not
the equivalent cost.
So you're not creating.
Okay, so you have one equivalence class, and then you have a count.
Yeah,
associated with it.
right, sure. So yeah, it's considered frequency actually.
So in the static analysis case, you would use some estimate of branch probabilities or something to get real numbers for.
This is dynamic analysis, it's not static analysis.
You don't try to do this statically at all, right?
Try to do it statically. That's little. I don't know. That's not quite straightforward for me. I don't.
You take this information and combine it with static, but you don't try to do it static.
No. So this is completely a runtime analysis. All right. So so far, all costs that we have talked about are cumulative costs that measure the effort made from the very beginning of the execution to produce a runtime value. So, however, we found that cumulative cost is not quite useful in helping programmers understand performance problems because it's almost certain that the value produced later during the execution has a higher cost than the value produced earlier during the execution, right? There doesn't exist a strong correlation between a high cost and a performance problem. So in order to solve the problem, we propose to compute relative cost instead of, cumulative cost. So the relative cost for a runtime value, like a heap value, is defined as the amount of work done on the stack that transforms values read from other existing heap locations in order to produce this value. I'll show this by example. Let's consider this picture where boxes represent objects, edges represent data flow. Those FG, HG represent object fields. Suppose now we want to compute the cost for O3. If we want to compute this cumulative cost, we only need to consider, so we basically need to consider this amount of work done, pretty much all the work done from the beginning in order to produce the values written into O3, right? All the work. However, if we want to compute the relative cost, we only need to consider this amount of work done on the stack that transform values read from other existing heap locations, like O1, O2, in order to produce the values into O3. So this is actually the fundamental difference between relative cost and cumulative cost. Completely symmetric to relative cost, relative benefit for heap value is defined as the amount of work done on the stack that transforms this value in order to produce values written into other heap locations. Let's consider again this example. So for example, now we want to compute benefit, relative benefit for O3. We only need to consider this amount of work done on the stack that transforms O3 into other heap locations like O4 and O5. So it's clear to see that relative benefit for a heap location is determined by both the frequency and the complexity of the use of that value, right? So eventually, the cost and benefits computed for individual heap locations are aggregated based on object structures in order to produce costs and benefits for high-level data structures. So this slide reveals some of the key problems and challenges and ideas in this work. So for example, to solve the first problem, dynamic slicing is too expensive. We propose to use a new technique called abstract dynamic slicing that performs dynamic slicing over bounded abstract domains. To solve the second problem, which is how to abstract instances for OO data structures, we proposed to use object sensitivity-based calling context as abstraction. To solve the third problem, which is cumulative cost is not correlated with performance problem, we proposed to use relative cost instead of cumulative cost. So combining all the three insights, we eventually compute relative abstract cost and a relative abstract benefit and use this cost-benefit ratio as an indicator to performance problem. So this analysis was implemented in IBM GNI virtual machine. And we performed case studies on the real-world large-scale applications. So in fact, all those applications here, except Bloat, have millions of lines of code. This picture shows the running time reductions that we have achieved after removing the problem that we found using this dynamic analysis, cost-benefit analysis. So for example, for Bloat, there is 35% running time reduction that we have achieved after removing the problems. This is actually the very first dynamic analysis targeting general bloat. All existing work target different kinds of symptoms, like symptom-based bloat. This is actually the only piece of work that targets the blend. Ben, you have
Can you go back to the,
sure.
The original example with the is package, and explain how it relates to this analysis. So, how do you compute the relative cost? Yeah, sorry about
all the way back.
Yeah. So.
Yep.
What ends up being the relative cost of whatever backs and relative benefit?
Well, so first of all, consider the relative benefit. The benefit is really easy to compute in this case because none of the elements in the heap locations, the heap values in this list are used for any purpose, right? So they're never used because you only use this reference value. You never retrieve the heap values from this list, right? So the benefit for this entire list is 0.
Not quite 0, right?
Yeah, it can't be 0. Well, I mean, 0 is.
I mean, it's,
yeah, I mean
for the data members.
Yeah, for data members, right? Exactly.
Equals whatever. Yeah.
Do the pass equals. I mean, this is a reference. I mean, this is the pointer value. This is not like the heap, the value retrieved from the heap location, right? So there is a large benefit. There's a large cost associated with the list because you compute all those files, you populate the list. So every data member in the list has a large cost associated with it, right? Because you do a lot of computations in order to produce values and then write them into that heap location, the list location, right? In this way, there's, it's clear to see that there's a large cost, but there's no benefit. I mean, very little benefit. So you get a large.
You can go on. I just.
Yeah.
I'm a little.
Or
some benefit because you have to test against string. Presumably, package name.
Yeah, we can.
Is a test, and that gets encoded in the result, right? If they match. Right?
Yeah, sure.
So,
Yeah.
Anyway.
Yeah, we can definitely talk offline. I mean, there's some subtle issues here. Let's go all the way forward. All right. So.
So can you get back?
Yeah, sure. Yeah.
So the bloat. So bloat is a constructed example, or is that a?
No.
Yeah.
Well, Bloat is a program analysis framework written by Purdue University, like many years ago. It's a large Java program analysis framework.
Why is it called bloat?
I don't know. It was the name of the application. It was included in the Decabo benchmark set.
Interesting. Okay.
Yeah, many years ago. So that's basically. Well.
Yeah, so did I. It's why I asked. Okay, thanks.
Well, the reason, I mean, why we can find this, such a large running time reduction is because Bloat is pretty much written by graduate students. So the quality of the code is really, it's really poor.
Can you talk? Was it one issue that you found in this, or were there multiple issues?
There are multiple issues. Yeah.
So there's not one that you could.
There's no. I can give you specific examples later offline. Yeah. All right. So this is actually the very first dynamic analysis targeting general bloat. In addition, in this work, we have identified a lot of interesting bloat patterns that can be regularly observed during the execution of large-scale applications. So, a further step would naturally be to develop a static analysis that can identify and remove such patterns in the source code so that the programmers can avoid such small performance problems during development, during coding, right? Before those problems really pile up and become significant. So in fact, some of the interesting bloat patterns that we found in this work have already led to the development of new analysis and the tools. So for example, I'll give you specific examples. We found a lot of interesting, container inefficiencies. So we developed a new static analysis that uses context-free language reachability formulation to help programmers identify underutilized containers and overpopulated containers. That piece of work was published in another PLDI 2010 paper. And we found there are a lot of loop-invariant data structures in this work. So we used a type and effect system to help programmers identify and hoist those loop-invariant data structures. Some other patterns that we found in this work include problematic implementations of certain design patterns and anonymous classes. So actually, the kind of work that I can do immediately would be to develop static analysis to deal with these patterns, like 3 months of work. All right, so now we're getting to the third part of the talk, which is actually the static analysis that can be used to help programmers identify and hoist loop-invariant data structures. The motivation of this particular analysis is based on the observation that in large-scale applications, there are a lot of places where objects with the same content in the loop get created many, many times by different loop iterations. And all their instances are exactly the same. It really hurts performance in many cases. So by pulling those objects out of loops, in other words, hoisting these objects in a semantics preserving way, we can potentially save a lot of computation as well as garbage collection effort, right? So that's basically the motivation. Let's first look at the example. All right. So this piece of code shows the problem in multiple applications, not only one application, like multiple applications that we studied in IBM T.J. Watson Research Center. So the loop here iterates over a string array called date. Date here is a string array. In order to parse each of the string in this array into a date object, right? So the way this loop is implemented is that it creates a simple data format object per iteration of the loop, and use this object to parse each of the strings. So it's easy to see that this entire data structure, reachable from this OSDF, which represents this allocation side, gets created many, many, many times, right, by loop iterations. So, and all their instances are exactly the same. In many cases, creating an object using this new keyword in Java is much more than allocating the space for the object. It can involve a lot of heavyweight operations to initialize a big data structure, like this one here, and create a lot of other objects, like this O1 and O2, right? So specifically for this case, creating one simple data format object requires to load many resource bundles from the disk, which can involve a lot of very slow disk I/O operations. So it's perfectly okay for us to pull this out of the loop and use only one simple data format object, data structure, to parse all the incoming strings, right? Yeah, sure. Yeah,
Well,
sure.
You said it's perfectly okay. That depends on a lot of stuff.
Oh yeah, sure. Yeah, of course we have. Yeah, I'll definitely go to. I mean, there's 5 or 6 different checks, like very specific checks over there. So it's not that simple. Not as simple as what I said.
So in this particular case, it's the case that parse treats SDF as a read-only object.
Mm-hmm.
Are there other mutating operations?
No, our static analysis can make sure that there's no.
On the class, on the entire class, is there any way to mutate a simple date format?
On the entire class. What's
Is
your
it a
question?
property of simple date formats that once constructed, they're immutable?
Yes, it's immutable, right?
I don't know.
I think so. Yeah, of course. I mean, no. I think that the only thing that is not immutable is you have to load sort of the current date from the date and the whatever the date and the time format from the local computer to initialize this big data. A lot of resource bundles loaded. Yeah, once it's constructed, it's immutable, of course.
So, could this be solved at the library level by having like a static factory method that yielded a singleton object that was only?
Oh, of course, you can definitely do that. Yeah, there's a possible way of doing that. Right. Yeah, there's definitely one possible way of doing this. Optimizing this case.
So is it often? I'll talk to you.
Well, okay. Yeah, but sometimes for library designers, they're not careful enough to consider this kind of complex cases. All right, so it's clear to see that the challenge, the biggest challenge in our work here is that we want to hoist a big data structure out of the loop instead of one single instruction or one single object. That is the fundamental difference between our work here and the traditional compiler loop optimization work. So given the difficulty of hoisting a big data structure out of a loop, we divide this technical problem into 2 sub-problems One focuses on the data side. One focuses on the code side. So the first subproblem here focuses on hoistable data structure. So which means that, first of all, for each object created in the loop, we need to identify this entire data structure, big data structure, that is reachable from this object. And then we check whether or not all fields in this big data structure are loop-invariant without considering any actual code statements that access this data structure. So if all fields in this data structure are loop-invariant, we call this data structure a hoistable data structure. Back to the example, our static analysis can make sure that this entire data structure reachable from OSDF is a hoistable data structure because no field in any instance of this data structure can contain iteration-specific value that can change across iterations. Our static analysis can make sure that happens. And once we have a set of hoistable data structures identified, the second step here tries to hoist the actual code statements that access those data structures. So the key idea here is that for each hoistable data structure, we check each call site that is invoked on this data structure and see if it's hoistable. If this data structure if this call site is indeed hoistable, we just pull it out. Let's go back to the example. Once we make sure that this entire data structure reachable from OSDF is a hoistable data structure, we check each call site that is invoked on each object in this data structure. So for example, we first check this allocation site because the allocation site is also call site, right? It's a constructor call. And in this case, the allocation site itself is completely hoistable, so we just put it out of the loop like this. And then we check the second call, which is the call to method parse. However, the second call here is not hoistable because the argument date here contains iteration-specific value, right? That can change across iterations. Our static analysis can identify that. So there's no way to hoist this second statement, the call side. So this is actually what the code looks like eventually after our analysis performs hoisting. So it's important to know that this analysis is an interprocedural compiler analysis. It's not a source-to-source translation or some form of refactoring. So this is completely a compiler analysis. All right, so let's first look at this first technical problem, subproblem, which is to identify, which focuses on the data side, how to identify hoistable data structures. So we found there are 3 challenges to identify a hoistable data structure. So the first challenge here is to understand how a data structure is built up. So for example, for each object created in the loop, we need to identify what other objects are reachable from this object. This requires us to reason about the point-through relationship, right? This is very simple, straightforward. The second challenge here is to understand where the data comes from. So for example, we have to make sure that no field in the hoistable data structure can contain iteration-specific value that can change across iterations. That requires us to reason about dependence relationships. And the third challenge here is to understand in which iterations the objects are created. So for example, a hoistable data structure cannot contain objects that can be created in different iterations. Otherwise, there's no way to hoist it. To understand this information, we propose to compute iteration count abstraction for each allocation site that can have 3 abstract values, 0, 1, and the bottom. 0 here means that this allocation site must be outside the loop. In other words, all instances created by this allocation site must exist before the loop starts. The second case here is if the ICA for an allocation site is 1, it's guaranteed that this allocation site is inside the loop, and no instance, the lifetime for any instance of this allocation site must be within the iteration where this instance gets created. In other words, no instance of the allocation site can escape the iteration where it's created to later iterations. And the third case here is bottom, which means that the allocation site must be inside the loop, and some instance of this allocation site might escape the iteration where it's created to later iterations, and may actually be used by those later iterations. So it's clear to see that we're interested only in data structures where the ICAs for all their objects are 1, right? Because it's guaranteed that all objects in any instance of the data structure must be created in one single iteration and all die at the end of iteration. So the ICAs for objects can be computed by a general technique called abstract interpretation. So this talk focuses only on those high-level analysis ideas. If you're interested in those low-level analysis details, we can definitely talk offline. Or you can read the paper. There are 4-page formalism and proof out there. All right, sure.
So you gave a motivating example in which you created an object that was immutable and also presumably the constructor depended functionally on, on things that weren't modified in the loop.
Right.
But you have a much more ambitious analysis here that's trying to identify that would handle objects that are mutable but not mutated within the loop.
It's mutable but not mutated in the loop.
I mean, you're defining the concept of loop-invariant, and there's nothing that requires the objects to be deeply immutable.
I mean, we have this dependence analysis to identify this kind of immutable fields. So it's immutable but not mutated in the loop.
No,
right?
Mutated.
It's not mutated.
So you could have a less ambitious analysis that would identify just completely immutable after construction objects, on a class basis.
Right.
And then it wouldn't matter what happened in the loop.
Mm-hmm. Sure. I definitely understand. Our analysis is more ambitious in terms of here, like to identify.
Do you find actual cases in which
the class is immutable, but is immutable, but is not mutated in the loop?
Where you get extra benefit over just a plain immutable?
Oh yeah, sure. Yeah, of course. Yeah. All right. So how can we identify those hoistable data structures? We combine. I mean, the interesting idea here is we combine the 3 abstractions in a powerful way by annotating points to and dependence relationships with ICAs. So here's the example. I don't know I have time to talk about this, but so how much time do we have, Ben?
I mean, we have the room till 12. So.
Oh, okay. So yeah, okay. I'll continue. So let's first look at the example. So this the very simple example that contains 1 loop and 4 objects. So let's first look at the ICA for each object here. So the ICA, for example, for O1 here is 0 because the allocation side is outside the loop, right? That's very easy. ICA for O2 is 1 because no instance of this allocation side can skip the iteration where it's created to later iterations, right? This is the same case for O3. But for O4, the ICA is bottom because some instance of this allocation side might skip iteration, right? The current iteration where it's created to later iterations, and may actually be used in those later iterations. For example, here. Right? So basically, 1, 0, 0 bottom are the ICAs for this 4 allocation sides. It's pretty easy to understand. This picture shows the annotated points to graph, where each node represents an allocation side, an object, and each edge represents an annotated points to relationship, which contains a field name, which is FGH, our field, and a pair of ICAs for the 2 nodes, 2 objects connected by the edge. So by reasoning about this points to relationship, like this annotated points to graph, we can easily conclude that this entire data structure reachable from O2 is not hoistable, because the ICA for O4 here is bottom, because there doesn't exist any way to hoist this entire data structure. This picture here shows the annotated dependence relationship, where each node represents either a heap location or a stack location. And each edge represents a dependence relationship annotated with a pair of ICAs for the 2 nodes connected by the edge. The ICA for a heap location, like O3.value, is actually the ICA for the object O3, which is 1 in this case. The ICA for the stack variable is actually determined by where the stack variable is declared. If the variable is declared outside the loop, its ICA is 0. If the variable is declared inside the loop, the ICA is 1. So the ICA for stack variable can never be bottom, because in Java, any variable declared in the loop must be initialized every time the loop iterates, right? So, for example, from this case, we can easily see that this location, O3.value, depends on a stack variable that can depend on itself, which indicates that this heap location can contain iteration-specific value that can change across situations. So any data structure that contains this location is not hoistable, so basically. We found there are 4 interesting properties in a hoistable data structure. Missing any of the properties here can make a data structure non-hoistable. So those 4 interesting properties are disjointness, confinement, non-escaping, loop-invariant. So I don't think I will have time to go through all the details. I'm probably going to skip those details. So if you're interested, we can definitely talk offline. So there's one important thing I can definitely report here. That is the verification of those 4 important properties can be easily done by performing checks on the annotated points to and the dependence graph. That's the only thing that you need to know to understand this piece of work. Okay? All right, so once we have a set of hoistable data structures identified, it's really easy for us to identify hoistable calls. You know, the actual code statements that access the data structure. This is actually the second step, right? I mean, the most important part of this work is the first step. As long as you understand the first part, it's really easy to understand the second part. So the key idea, again, is to, for each hoistable data structure identified, we check each call site that is invoked on the data structure and see if it's hoistable. This process can involve, like 1, 2, 3, 4, 5, 6 different checks, like control dependence checks, argument checks, external environment checks, stepping stone, threat control flow checks. As long as all those checks are satisfied, this particular call site can be hoisted. So I'm not going to talk about all those details, as they're very specific checks. They're defined clearly in the paper. So we can definitely talk offline if you're interested. So that's pretty much about this automatic work, the sound and automatic transformation. However, we found that this completely sound and automatic transformation is not quite effective in hoisting real-world data structures. There are basically 2 reasons here. First of all, the real-world usage of Java data structures is very complex, and any static analysis has to be over-conservative to achieve safety, right? And the second reason here is that hoisting a lot of real-world data structures requires developer insight. So for example, consider a data structure with 100 fields. If there's only one field that is not loop-invariant, this can make this entire data structure non-hoistable. However, if this information is given to the developer might have a way of hoisting the data structure. Right? For example, the developer might be able to split the data structure into a hoistable part and non-hoistable part, right? And pull out only the hoistable part. So in order to make our analysis more practical and help programmers perform this kind of manual hoisting, we propose to compute hoistability measurements for each data structure in the loop that indicates how likely this data structure can be manually hoisted. So for example, we consider metrics like data hoistability and code hoistability. I'm not going to explain all those details again. They're defined in the paper. So we can definitely talk offline. But there's one important thing, which is the computation of those hoistability measurements fits nicely, very nicely, with the original analysis that we proposed for transformation. In other words, we don't need any new analysis to compute those measurements. They're computed automatically with the transformation, the actual transformation. So the analysis was implemented using the SUIT 2.3 framework and evaluated on a set of 19 large Java applications. In these 19 large Java applications, a total 981 loop data structures are considered, in which we found 155 data structures are completely hoistable data structures. However, our completely sound and automatic transformation was able to hoist only 4 data structures in 3 programs completely automatically because of the 2 reasons that I mentioned. So here's the list of the running time reductions that we have achieved after hoisting those data structures completely automatically. From those numbers, we can easily see that there's a large optimization opportunity out there, but only a small portion of it has been captured by this completely automatic transformation. To exploit the rest, we do manual hoisting with the help of hoistability measurements. Yes?
So if I understand this correctly, you're saying you improved the performance of Java C by 10% by hoisting something out of a loop, basically?
Java C, no, yes.
So what was the data structure that gave you that benefit?
I don't know, actually. This is a completely automatic analysis, and Java C is not open source. So I saw, I used analysis to produce a new bytecode, a new version of bytecode, and then I run the new version, and it got this 11% running time reduction. I don't know what's actually going on there.
Okay.
So
you actually, okay.
this is not open source. This you can't get the source code for this application, JavaScript application. So. But we do have open source. Do have source code for some other applications. So we studied 5 large Java applications by inspecting top 10 data structures ranked based on hostability measurements. We've actually achieved much larger performance improvement than this completely automatic transformation. For example, for applications like PS, which is a PostScript interpreter, we're able to make the application run more than 6 times faster after hoisting only a few data structures in these core components. And as another example, for applications like Zelan, which is a real-world XML transformer processor, where there's a 10% running time reduction after we hoisted only one XML transformer object out of a loop. So this sort of a performance bug has been confirmed by the decoupled development team. So there's one, for this case, we hoisted only one XML transformer object. So.
What did you do to PS to get the huge?
Yes.
What was hoisted?
We found there's the problem is actually with the usage of the data structure called the stack. The programmer seems to understand. They don't understand the stack is a subclass of the list. So every operation they want to do with stack is they use push and pop. So they keep pushing and popping stuff from the stack. They don't understand the stack is a subclass of a list. So they can directly use something like get to retrieve a specific element. They use put.
So was that a change in the code beyond just pulling it out of the loop, or what was?
Yeah, there's something more complex going on there. So there's not just hoisting the data structure, but we found this problem by identifying the hoistable data structures. Okay. So. We found there's no problems that we found in this work have ever been reported before in previous work. So, all right, so we're getting to the final part, which is future work and conclusions. Of course, I'll continue this line of work on software bloat analysis because I think it's a wide open area that has so many interesting problems, challenges, and potential research opportunities. We're actually one of the very few academic groups that are doing fundamental research on this real-world problem. Why do I think this is a wide open area? Because if you look a little deeper into the cause of the bloat, you will see that the methodology of object orientation itself encourages a certain level of excess or bloat. So for example, the programmers are encouraged to basically do whatever they want to do favor reuse, modularity, readability, leaving performance entirely to the compilers and the runtime systems. However, if we want to advocate to explicitly consider performance, this can have impact on almost the entire software development cycle, right? So this picture shows the kind of work that I'm planning to do in the future. For example, we start with detecting performance problems. So once we find, the root cause of those problems, we can either do manual tuning or we can classify interesting bloat patterns. Once we have a set of interesting bloat patterns identified, we can do a lot of different things. We can develop a static transformation that can automatically remove such patterns in the source code. We can develop a self-adjusting systems as part of the feedback-directed compilation that can remove such problems online as part of the JVM, right? Or like the CLR or the runtime in the Microsoft setting. We can advocate performance-conscious software engineering that can require a whole lot of new things. New design principles, new modeling tools, new testing analysis tools, new compiler supports, and so on and so forth. And we can also use a compiler to synthesize a bloat-free implementation given a set of performance specifications. So there are a lot of interesting things we can do in the future. In addition, I'm also considering to leverage existing techniques from other fields, such as systems and architecture, in order to deal with this ever-increasing level of excess or inefficiencies. Of course, I'll also look into other program analysis, actively look into other program analysis areas. So definitely one of the things is to adapt existing techniques to solve Microsoft-specific problems. Like for the existing techniques, all the existing techniques are implemented within JVM. So is there? So what are the problems that are specific to Microsoft products? Is there a possible way to adapt those techniques into this CLR, within this Microsoft family of languages? Is that possible? I don't know. So definitely it's interesting to see. There are some other interesting things that I'm planning to do in the future, like parallelism is definitely one of the most interesting things. Still, like optimizations, database compilation, model checking, testing, debugging, security, privacy, compilers for high-performance computing, data locality. I mean, the bottom line here is that I'm open for collaboration with any researcher whose research deals with the static and dynamic program analysis. That's pretty much my goal. So the conclusion here, I'm a program analysis person. I'm interested both in theoretical, static and dynamic analysis, and both the principles and applications of the program analysis. My dissertation here deals with an important application, which is software bloat analysis, that contains both dynamic analysis that can help programmers make more sense of heaps and executions, and static analysis that can help programmers remove and prevent bloat. So with a set of techniques that I have developed, I hope that we can lower the bar for performance tuning. In other words, with automatic tool supports, I hope that tuning is no longer a daunting task. I also hope to educate the programmers, the developers in the real world, especially the OO programmers, and to raise the awareness of this bloat problems in the real world object-oriented programming. So for example, the developers should really be aware that performance is important. They should do everything possible during development to avoid small performance problems before they pile up and become significant. So this is because compilers and runtime systems are not always smarter than human experts. All right. Thank you very much. I'm ready to take questions. Yep.
I have one question for you.
Sure.
So in all the work that you talk about, you really didn't talk at all about the hardware or the cache, sort of memory hierarchy as a source of performance bottlenecks. Is that something that you intentionally didn't investigate? Are you interested in investigating it? How does your work relate to that?
Well, actually, I didn't get any chance to investigate that. I'm interested in doing that, definitely. So, yeah, I mean, for example, the cost-benefit thing can be the current definition of cost-benefit is defined in terms of computation, right? The amount of work done to produce a certain value. It can naturally be extended to work for like the cache and other things. I don't know how to do that, but I think it's doable. Yes, I mean, the answer to the question is that I haven't done any work specific to the cache and the memory hierarchy thing. So all the work that I've done are related to program analysis. That's the only thing that I have done.
Any other questions?
Yeah.
For the first part of the
cost benefit.
So you gave a motivating example in which there were a series of writes that were never read. Mm-hmm. And you had a considerably more ambitious framework for measuring the cost benefit.
Right.
And did you quantify? I mean, you can imagine a simpler one that would just identify writes that were never read.
Oh yeah, sure.
And are you able to quantify how much extra benefit the extra ambition gets?
Oh yeah, sure. I understand your question. Well, I mean, we do find sort of more complex cases where the benefit part is not just like no use. So I'll give a very specific example. We found that for a lot of data structures in large-scale applications, they're just purely copied from one source to the other source. Like if you consider those large-scale web-based applications, they have different components may have different representation of the same piece of data, right? So in order to be transmitted, for example, for J2EE applications, in order to be able to be transmitted on the network, they have to be wrapped into the SOAP sort of protocol. So some piece of data keeps being wrapped and unwrapped in order to be transmitted between different components. So our analysis can perfectly find places like that So, for example, a piece of data is wrapped in this application, is this component, but it's unwrapped in that without any computation done. So, and then there's definitely a lot of optimization opportunities out there. So we did find a lot of cases, more complex cases, than the simply like no use. Yeah. Yeah.
Okay.
Thank you. Thank you very much.